set of 10 lectures, each during 2 lectures per day. And the schedule for January specific dates will be decided probably today.
Yeah, we'll see.
So please start.
Okay, so thanks, Misha. Okay, I'm very happy to be here. This is a course that I've been teaching that has been growing actually over 15 years of teaching at SISSA in Trieste. And I did experiments with students everywhere in the world, in India, in the United States. It's the first time I give this course in Slovenia, and so, well, you will see. I will discuss briefly the content now, but to start with, I would like to invite you, in case you don't understand something, not something major, but something minor, please stop me and ask the questions. I mean, the problem I have with Italian students is typically that they don't like to ask questions. I don't know why. It's a cultural thing, and they think that asking a question, they will be judged by the quality of the question. This is not the case. This is not my case. This is not the way I grew up with. So in case you really don't understand something, please stop me. You're allowed to ask anything. That's what I wanted to say. Now, it's a course on what the heck? Yes, okay. Non-equilibrium. Many-body physics, and for quantum systems. Now, there are 2 parts to this course. The first part concerns thermally isolated systems. And the second part concerns open systems, or in general, transport. Now, the first part is actually discussing mainly stuff that was done in scientific research over the past 20 years, so which concerns the dynamics of really quantum thermally isolated systems. And a big chunk of it is the physics of so-called quantum quenches. And I hope you're aware that here in Ljubljana, there are quite a few researchers who contributed a lot to this field. Tomasz Prosen, Ilieski, etc., etc. So this is one thing that I will be doing, and it will take roughly 5 lectures. The total is 10. And then the second is open systems, physics of transport. This is more standard. So I will be teaching you essentially with a peculiar approach, the so-called Keldysh technique. That is a technique that was invented to extend field theoretical methods to non-equilibrium problems by Keldysh, and with some contributions by other people. And it's, typically my experience is that students are somewhat scared by this sort of, with the exception of Russian students, they're somewhat scared by this sort of technique. But it's actually something rather simple the moment you understand how it works. So I will try to teach it with a hands-on approach, by solving specific physical problems related to transport in many-body systems. And my hope is that by seeing how this technique solves simple problems, you will understand also how it works, and will be ready to take standard books of many-body physics to actually try yourself to do calculations. Now, concerning literature, since we are discussing things, now on the Keldysh technique you can find tons of things, starting from Landau Lifshitz, the book on physical kinetics, etc., etc. So my hope is that I will take you to a point in which you will understand the basics, so how it works, and you will be able to read by yourself a book that I like a lot by Alex Kamenev. That is called, I think, Non-Equilibrium Quantum something. It's a very nice book. So my goal is to just give you the basics, and then you will take Kamenev and you will read it by yourself. Okay? So the peculiarity of the book by Alex is that he does the Keldysh technique, which is a field theoretical technique using a path integral. I will not be using the path integral because, in my opinion, if you see first the Keldysh technique with the path integral, well, it's not clear you will understand everything, right? There are some details that are too complicated. So I will be using another approach, but after you understand what is the meaning of all green functions, you will be ready to read this book and study it by yourself. Now, concerning the first thing, there are plenty of things to say about quantum quenches, simply because it's 20 years that people do research on this subject. Now, there are some standard reviews on this. One is a 2011 colloquium that I wrote with Tolya Polkovnikov. Et al., and I am one of the et al.s. Then there is another review, 2011 and 19, sorry, always by Tolya Polkovnikov. Et al., and it's a different set of et al.s. Always 3 et al.s, but it's a different set. In which case, and then you see that since he's always the first name and it's always in alphabetic order, he's selecting the other authors with letters that are following the P, essentially. But so Tolya is really one of the main persons who has been thinking about this subject in a broad sense. So you can check his works and his reviews, and he has tons of material that you can read and study. And there is another thing you might be interested in, if you can find it online. It's a JSTAT volume. JSTAT is a Journal of Statistical Physics. It's actually published at CISA, so that's why I know it pretty well. This was edited by Pasquale Calabrese et al. And for all that concerns a topic that is related to integrability and quantum dynamics, generalized Gibbs ensemble, etc., is a topic that I will only very vaguely touch in my lectures because it's very technical. You can read a lot about it here. Okay, so I think we're essentially done. So we are going to start with the first topic, so thermally isolated systems. And I'm going to take a few lectures on this. So, so now I have to manage to, I'm sorry, but I have to get used to this one way or another. All right, so thermally isolated systems. So first of all, what are thermally isolated systems? In physics, there's not a single system that is thermally isolated. You're always coupled to some environment, but luckily there are some physical systems and emerged in the past 25 years, some physical systems that to a good approximation are thermally isolated for the duration of the experiment. Examples, cold atoms in optical lattices, ion traps, etc., etc., etc. You know it better than me, I suspect. So in all these systems, we can do experiments of dynamics that to a good approximation are, can be described just by the standard Schrödinger equation. You don't need to use Lindblad, you don't need to use Keldysh, you don't need to think about an environment, you just think about a classical, a quantum system described by a quantum state that is propagated forward in time using standard Hamiltonian evolution. And by the way, this was true until a few years ago, because now it's very popular to even think about a coherent time evolution of your system that is not Hamiltonian at all. For example, you can think of having a register of qubits, and you can think of applying a set of unitary gates to your qubits in a kind of brick wall or non-brick wall sequence, and that will propagate forward in time. It's not really time, of course. It's a sort of discrete time, your state. And you can do measurements in between. You can do many interesting things. We will be touching this towards the end of this lecture. But overall, it's a problem that is slightly different from what people were used to until, when I was doing my PhD, so late 90s, beginning of 2000s, when the main goal was to describe transport, and when you describe transport, you're always dephasing, dissipation, and you have to think about all these issues. Now, you can tell me, why is this interesting? Well, of course, it's not that, it's not that interesting if you look at it. It's just a Schrödinger equation and unitary propagation. It becomes interesting the moment you start doing this for thermally isolated many-body systems. So, for example, so you can think of taking your favorite many-body system that is described by an Hamiltonian that depends on a system parameter, and you can think of changing this parameter from some lambda initial to some lambda final along a certain protocol, lambda of t. So it could be an abrupt variation, could be a linear variation, could be whatever you want. Now, in the case it is an abrupt variation, it's called a quantum quench. In the case it's a slow variation, people call it a slow quench, but it's, quench doesn't mean this in English. So I will try not to use this word for other protocols. What could be this Hamiltonian? Could be whatever you want. Could be lambda, could be the BCS coupling in a superconductor, or it could be the transverse field in a transverse field Ising model. And now the question you're facing is, I'm doing this, so I'm taking my system out of equilibrium in the sense that I'm changing the parameters, and I want to see what happens. So what is the effect? How do I describe what is going on my system when I take it out of equilibrium? What should I calculate? Now, technically, there have been three ways to address this problem in the literature. And the first way is to study these protocols, or this sort of non-equilibrium physics, the way you would study the same physics in a classical system. So if you were in a classical system, you would study this physics using either stochastic thermodynamics or thermodynamics, if you don't like to go into microscopic details, but you would try to do a thermodynamic characterization. Another way to look at this problem is to look at it from the point of view of condensed matter physics. Now, in condensed matter physics, whenever you have a problem, yes?
What exactly do you mean by thermodynamics?
Well, you compute, so we will be starting with this, but you compute, for example, when you change the parameter, how much work you're doing on your system, how much entropy is produced, what is the entropy production, what is the heat that is dissipated, etc., etc., etc. So another thing you can do is focus on quantities that you typically compute in condensed matter physics. Now, condensed matter physics is essentially done with response functions. Response functions are correlation functions. So you can start computing correlation functions, correlators of some local operators that are your observables, or you can compute the expectation value of your observables or higher order correlations, whatever you like. In this case, well, this is exactly where the interplay between integrability, ergodicity, etc. came to play a role in this game. You start seeing details of the dynamics that are related to the emergence or the non-emergence of well-defined quasi-particles. So you can get some information that is related to really the condensed matter, typical condensed matter-like structure of your system. So quasi-particles, integrability, etc. And you know that integrability plays a major role in the dynamics also of classical systems, because I'm sure that all of you are aware of the standard Fermi-Pasta-Ulam numerical experiments that has seen that in a non-harmonic chain of oscillators, you can still get the lack of equipartition because of various mechanisms that are that it took a lot of time to understand. Now, another thing that became popular to do in this field was to study quantities that are at the interface between condensed matter physics and quantum information. So I'll call it quantum info inspired. And here we will have, so for example, the entanglement entropy, the quantum Fisher information, multipartite entanglement, and at the end, a strange object that is called the OTOC, out of time order correlator, that was introduced by Alexei Kitaev in order to detect, well, I will explain it in detail, but to detect how much quantum is a system that looks ergodic from all points of view, looks thermal from all points of view. Anyway, okay, so what I'm going to do now is I'll take the path as I wrote it. So I'll start with thermodynamics, then I will explain very briefly the story of correlators. Now, for correlators, there are essentially two subjects. One is the generalized Gibbs ensemble, and one is the eigenstate thermalization hypothesis. Since here you're sitting in the middle of world experts of generalized Gibbs ensemble, and I mentioned them before, I'm not going to tell you anything about the generalized Gibbs ensemble, only something very, very short. And in case you want to know more, you ask Tomasz Posen and others, and they are able to give you a much better coverage of the generalized Gibbs ensemble than myself. And I'd rather tell you something more about ergodicity and how it is described in quantum system using the eigenstate thermalization hypothesis. All right, so now, oh, I made a mistake. 4, move up, up. Okay. Okay. So, now we have to decide, so we have to figure out how to characterize thermodynamically these quantum quenches. So we again have an Hamiltonian. Oh no, what the hell? It's so much better with choke, right?
By the way, I think in this mode you can use the back of your pen. Don't switch the mode, just use the back of your pen. Then
Oh, the back. No.
No, oh, okay, unfortunately.
No, the problem is that I'm used to teach with choke. So whenever I write something stupid, I use my hand to raise. No, but now it's in the razor, right? I do this, and I do that, and then I do this, and then what the hell?
Try just with your palm. Oh, yes.
Ah, wow. Fantastic. Okay, I will buy it then. Okay, good. So what I wanted to say is that you have your quantum Hamiltonian. It depends on a certain parameter, and you change these parameters from some lambda initial to some lambda final in time according to a certain protocol. And now we want to characterize thermodynamically this process. So what would you do if this was not a quantum problem but a classical problem? So you all know that in classical physics, well, so when you're taught thermodynamics, they tell you that you have a thermodynamic state at A in your parameter space, x1, x2, x3. You have thermodynamic state at B. A thermodynamic transformation is a certain path that goes from A to B in parameter space according to a certain protocol. And the way you characterize the properties of this transformation is by computing how much work was done on the system, how much entropy was produced, the change in free energy, the heat that was dissipated, etc., etc., etc. Now, let us focus on the work. Well, it's pretty well known already at the level of classical systems that, so typically when you're taught standard thermodynamics in undergraduate classes, you're taught that when you do a thermodynamic transformation, you do a certain work on your system. I raise this chair, I'm doing a certain work by bringing it up against gravity. Now, but if I do the same thing, instead of raising a chair, I try to raise a protein that is in a folded state attached to some substrate here and sitting in a solution, by putting here on top, for example, a positive ion and applying an electric field, how would I measure work? Well, I would measure work by applying an electric field, see how much the protein stretches, and multiplying the force by the length, right? That's the standard definition of work. Now, the point is that if you do this experiment, since this is roughly a mesoscopic system, what you would see is that if you repeat this protocol many times, every time you repeat this protocol, you will get fluctuations on the length your protein is stretching, right? So, and these fluctuations you can translate into a probability distribution for the work that is done on your system. So in other words, work is not well defined for microscopic system, it has fluctuations. And this is something that is pretty well known in a classical system, is the subject of something called the stochastic thermodynamics. I don't know if you have ever heard of this, but there are very nice reviews that you can find in the archive. The one that I remember is by Seifert. Okay? Yes?
We're talking about not like quantum fluctuation.
No. This is just thermal fluctuations, right? Or stochastic fluctuations due to the solvent, etc., etc. Now, what about quantum systems? Now, in quantum systems, now I'll try the technique. In quantum systems, you have a similar story. Let us think about the simplest possible thermally isolated system. We take the only exactly solvable non-equilibrium problem in quantum mechanics. Well, it's not the only one, there are a couple, but this is one of them. It's called the Landau-Zener problem. So T here is time, V is the velocity with which you're varying your energy level, your diagonal energy level, and delta is some coupling. So you should think of this as a function of time, as two energy levels that are coming one against the other, and because of delta, you have an avoided crossing. So this is delta, right? So if this was spin up and spin down, so that's what happens. Right, so this problem was studied by, as I mentioned, by Zener, who solved it exactly, solved the Schrödinger equation using parabolic cylinder functions. You can find this paper in the Proceedings of the Royal Society. It's a very nice paper, but very technical, as you can imagine. And it was also solved by Landau, who actually was writing a paper about collisions of molecules. And at the end of this long paper on collision of molecules, he says, if the molecules have also an internal state, then the probability to flip the spin gives the result. No calculation, nothing, right? So typical Landau style. So the point is this: if you have this process and you ask yourself, what is the probability to end up in the excited state? So to go across this as a function of time, start from minus infinity, goes to plus infinity, and then end up in the excited state, you will have that this probability is exponentially small, 2 pi delta. I'll mess up. I'm sure I'll mess up. Is delta over v squared. Okay. I always get it wrong. So let us think. If delta is large, v is small. Yes, no, it's correct. Okay, right, and the probability, so this is the probability if you start up to end up down. It's too big. Probability if you start up to end up down, and the probability if you start up to end up is of course 1 minus this. So you see something interesting here, that if you run this experiment, and you can do it, of course, if you start, so this is a standard example of the adiabatic theorem in quantum mechanics. Yes?
Just before I go to the next topic, I want to understand better how is it connected at all to collisions of particles?
Because when you're, okay, I think the way he was thinking about it, okay, this is my interpretation, okay, you know, is that when you have two particles that come close, they get into the scattering region and then they get off asymptotically, and then you're isolating only the internal degrees of freedom of it, nothing else. So roughly speaking, he was thinking about the internal degrees of freedom up and down as doing a process of this type. Don't ask me how and why. So
Because in quantum mechanics there was collision, in PFT there are collision, but I never heard that this is about collisions.
no, okay. Read the paper by Landau, okay? So just go read the paper by Landau and then we discuss it next time. This is what I understood from that paper.
Sorry, that's probably delta squared or V, because V is
Okay, so that's what I was telling you. I always get it wrong if I go
So
by
delta is
memory.
energy and V is energy squared.
Yes, you're right. So I was, okay, that's correct. I was remembering a square somewhere, but I was not remembering which way. So I wanted to check it, but then I was satisfied that it goes to 0 in the adiabatic limit. Sorry, it goes to 1 in the adiabatic limit. Anyway, okay, so what did I want to say? Right, so let us think about this now thermodynamically, right? So we want to ask ourselves how much work was done on the system by taking it across this avoided crossing. So one way I could define work, since it's a thermally isolated system, is by the change in internal energy of the system itself. Now, but then even defining the change in internal energy is not that straightforward, right? Because the change in internal energy, okay, so practically, how would I measure it? I would have to measure the initial energy of the system, do the protocol, and then measure the final energy, compute the difference, and that is the change in internal energy that I get. So in other words, what I'm trying to say is that if you want to define what is the work that was done on this system by this double energy measurement, you would have in practice to say that your work that you measure has two possible values. One is, delta E up plus infinity minus E down minus infinity, E up minus infinity, times P down up, no, P up, and then plus delta E plus infinity down minus E minus infinity up, P up down. Right? So that's how you will practically define your work, right? So is it clear? Work is just a difference in internal energies for a system that cannot dissipate, because of first principle of thermodynamics.
What about dimensions?
Dimensions in which case?
I mean, Newton times meters of work. I mean, we use different meaning of work, but
No, so first principle of thermodynamics tells you that the change in internal energy is the work that was done minus, well, depending on the convention you use, minus the energy that is dissipated, right? So since it's a thermally isolated system, I say, okay, this is 0. So what is the change in internal energy? Change in internal energy equal to the work that was done, nothing else. So there is nothing else, right? So how do I measure it? I have to measure an initial energy and the final energy. So my experimentalist, my friend who does the experiment, will have to measure what is the initial energy of the system, what is the final energy, and see what is the difference. And that will define a probability distribution in general. In this case, it's super trivial, right? Because it's the simplest possible protocol I can think of. If I have a many-body system, it's not going to be super trivial. Is it clear? No.
No, and the function gives infinity, right? So p equal to.
Ah, okay. You're worried about.
No, not only about this, the second question. First question is how it's ready to work in the.
This is distribution of work.
Distribution.
Is a work distribution, is a probability distribution, right? So delta function is not a problem because you have to integrate it, right? So the probability to have a work that is between E0 and E1 is going to be equal to integral dE dW PW, and therefore you see that everything is fine with dimensions. Okay? Good. Thanks for the question. Now. Okay, so this is the stupidest possible. What did I do?
The board is a bit stupid, so when you're moving something, it's thinking about the second.
Okay. So now, okay. So now now that we understand what in principle you have to do for this simple protocol, let us think in general, okay? So I have a system. Let us focus for a second on Hamiltonian dynamics. So a system that depends on a certain parameter. I'm changing my parameter from lambda initial to lambda final according to a certain protocol, and I want to compute what is the work distribution. So we decided, the only bottom line of what I said before is that since it's a thermally isolated system, I can define work by doing an initial energy measurement and a final energy measurement. Okay, so this is the only, yes?
Who is doing this work?
Who is changing this parameter?
Self-quantum fluctuations?
No, it's not quantum fluctuations. I mean, there is an external agent who is changing physically the parameter. So for example, well, so the external apparatus, right? So whatever. You don't describe who is doing this work. But there is something that is doing this work. Right, so now, in practice, how do we define it? So we said we have to perform an initial energy measurement at time 0. So at time 0, our Hamiltonian is H initial, so is H lambda initial. It's going to have some eigenvalues En lambda initial, some eigenvectors psi n lambda initial, and I'm going to do an initial energy measurement. I'm assuming that initially my system is in thermal equilibrium. So what I will obtain is a probability to measure En lambda initial that is equal to e to the minus beta En lambda initial divided by z. Okay? So if it's in thermal equilibrium, I do an initial energy measurement. I will pick an eigenvalue En with this probability distribution because I have a Gibbs density matrix. Okay? So now,
You mean that n in the lower index of exponent?
it's always the same. Sorry, I tend to be sloppy. Okay, it is always the same. You're right. No, okay. I wanted to raise and okay. It is always the same, right? N is n. So now no. Okay. So once I measure this, I do the protocol, right? So I do the protocol, and then I do the final measurement. And the final measurement is going to give me the probability to measure So in the final Hamiltonian, I will have some h lambda final, some eigenvalues em lambda final, and some eigenvectors psi m lambda final. And I'm going to have a probability to measure the eigenvalue m conditional to the fact that I measured in the initial measurement the eigenvalue n, right? So Pn m lambda, well, whatever. I don't know which notation I used, no notation. And this is going to be psi m lambda final. Then here you're going to have the time evolution operator, and then psi n lambda initial squared, where this u of t is equal to time ordered e to the minus I integral between t initial, t final, dt prime, h of t prime. Okay. So now that I have these two ingredients, I put everything together. What is the work probability distribution? The probability distribution of doing a certain work, W, is equal to the sum over n and m of the probability to measure n in the initial measurement times the conditional probability to measure m if I measured n in the initial measurement times delta of W minus em lambda final minus en lambda initial. And if you put everything together, you will get that this is equal to sum over n and m, a very simple expression, e to the minus beta en lambda initial over z times the matrix element times the delta function. Okay? Straightforward, right? I mean, I didn't write anything impressive. So this is as general as we can be for a thermally isolated system for this two energy measurement protocol. Now, the story becomes slightly more interesting because up to now it's not very exciting, I have to admit. If instead of computing the probability distribution itself, you compute the generating function of it. Let me define it as z of u. I'm not using the letter z by mistake. It has a purpose, because we will see later on that it can be interpreted for certain systems as a partition function. Anyway, e to the minus iw u averaged over p of w. Now, if you do the calculation using this expression, and I leave it to you because I'm sure that you're all better than me, at the end of the day, you will get that this is equal to the trace of u dagger e to the minus I h lambda final u e to the I h lambda initial u e to the minus beta h lambda initial over, no, over Z. They managed to simulate also the noise of the choke.
Use a matrix or is it unitary or?
U is the time-ordered exponential.
Oh, okay.
This is it. It's a standard evolution, so it's an operator. Right. So this is the expression, and this is Z of lambda initial. So let me write it like this. Now, usually when I teach, I get people confused because I'm using the letter Z for the generating function and the letter Z for that partition function. And so I found a way to call this a glorified Z to distinguish them. Otherwise, people mess up. Anyway, okay. So now, what can we do with this? Well, of course, you know that if you have a generating function, you can compute all moments, you can take the log and compute all cumulants of the probability distribution. But one interesting thing you can do with this is do the following. Imagine that I take Z of minus I beta, so which is equal to the average of e to the minus beta w with respect to P of W, right? Correct? You all agree. So now, let us plug it in that expression. This is trace of U dagger e to the minus I, sorry, not e to the minus I, but so minus I beta minus I will e to the minus beta h lambda final U. Here I will get e to the beta h lambda initial, e to the minus beta h lambda initial divided by z lambda initial. So this goes with that. And then I use the invariance property of the trace. So U dagger U is equal to 1. And I will get trace of e to the minus beta h lambda final divided by z lambda initial. So this is equal to z lambda final divided by z lambda initial, which is equal to e to the minus beta delta f, where delta f is the free energy lambda final minus the free energy at lambda initial, both with inverse temperature beta. Okay? Have you ever seen this? And just to gauge your knowledge on this subject. So this equality has a name. It's very famous. It's not worth a Nobel Prize, but it's worth a Wolf Prize. And was discovered by Jarzynski. Okay, now I'm messing up because I never know where the Y goes. I'll write it. I apologize to Jarzynski if I make a mistake. Jarzynski equality. And it's the statement that the average of e to the minus beta w with respect to P of W is equal to e to the minus beta delta F. Okay? Now, it is a very simple statement. We proved it for a quantum system, for a thermally isolated quantum system. Jarzynski originally proved it for a classical system. It is true for quantum systems, for thermally isolated quantum systems, for systems that are weakly coupled to an environment, quantum and classical. It is a very general equality. Actually, well, there are two guys whose names I don't remember who discovered it first. Discovered something very similar first, but it was not that simple. Now, it is very non-trivial for the following reason. When I take a system that is initially in thermal equilibrium, so it has initially a density matrix that is e to the minus beta h, and I time evolve it with a certain protocol, right? So I do, so this is rho of beta, I do u dagger, no, not u dagger, u e to the rho of beta u dagger, and I get rho of t. Well, this final state is not a thermal equilibrium state. It's not a thermal equilibrium state in general, right? It's not. It's some messy thing out of equilibrium with correlations, very complicated, etc., etc. Nevertheless, the Jarzynski equality tells you that if you compute the probability distribution of work, starting with this initial state, and you average e to the minus beta w, you will get the exponential of minus beta times the difference in free energies of the initial of the free energies relative to the initial and the final values of the parameter, as if the final state was in equilibrium at inverse temperature beta. Okay?
So I have more or less to think about it as a way how to compute the delta.
The delta. Well, yes. So in a sense, yes. That's how they use it in quantum chemistry. So it's but conceptually, at least for me, I don't do numerical simulations. It's a very interesting equality by itself. And it's very surprising that it was discovered only in 1997, right? Because it's such a simple result. It's very, yes?
Would it stand correctly to mean we have ensemble of two-level systems, they have one energy, then we apply our change of parameter, so system takes some energy, and how much energy it takes, there is some distribution of something, and that's why there is averaging, and that's how we get this increase in free energy. That's what it's meant.
Yeah, but the way you, so if I interpret what you said, I am extrapolating what you said. The way you think about it is you have an ensemble of two-level system, you give some energy, they equilibrate, and then you compute the difference in free energies. And what I'm trying to say is that this equality is true even if in the final state you have no equilibration at all. Even if the final state is an out of equilibrium state with a very messy energy distribution, no equipartition, nothing. Right? I don't need to have equipartition in the final state. I don't need to have thermal equilibrium in the final state in order to have this equality.
But if you don't have thermal equilibrium in final state, what is the free energy?
Well, that's what I'm saying. So what I get is that this is the free energy. This free energy is defined as the free energy at inverse temperature beta. Who sets the inverse temperature? The initial state. With the final value of the parameters. And this is something well defined, right?
So it's like just T logarithm Z?
Yeah, exactly. That's what it is. Other questions? So nobody's surprised. No surprise from the Jarzynski equality. I don't know, when I saw it for the first time, I was very much surprised. Anyway, so now, there is an interesting thing about, so there are some instructive and useful exercises that you can do on this subject. So I will just give you a few, right? And I mean, I'm not supposed to grade anything. I don't know. I mean, I have no idea. Misha didn't tell me anything. So, but if you want to do it, you do it. If you don't want to do it, you don't do it. It's up to you. My impression is that if you do calculations, you understand better the subject. So the first exercise you can think of doing is of course the simplest possible system, which is an harmonic oscillator. So p squared over 2 plus omega squared x squared over 2. H bar is equal to 1, everything is equal to 1, etc., etc. And now what do you do on this? You imagine doing a quantum quench in which you take the frequency from some initial value to some final value abruptly in time. So at time t equals 0, you do your quantum quench. And now, right, the question is, so let me see if I can find a question. So one thing you can do is, one, compute the generating function z of u and the probability distribution P of W, that is of course going to be discrete in this case. And consider, one thing you can do is consider the average work that is done as a function of omega initial and omega final, and consider the two limits, one in which, so limit 1, case number 1 is which is the limit omega I going to 0, compute W, and limit number 2 omega F going to 0, and you compute W, and give a physical interpretation of the results that you obtained. Now, this is a straightforward calculation. For those of you, you can do it at least in 3 ways, 3 possible ways. You can do it by deriving a recursion relation for the matrix elements that emerge in the probability distribution P of W. You can do it using squeezed states, if you're familiar with that in quantum optics. You can do it brute force. You will always get the result, and I think it's very interesting to solve step number 2 because it gives you also some understanding of the fact that the probability distribution is actually asymmetric in general. It's not granted that if you will go from some omega initial to some omega final, and if you do the opposite, you will not get the symmetric probability distribution in general. Okay, so now the question is,
It's thinking when you move it.
okay, good, think. Okay, so now the question is, right. Well, if you think about it, this equality is the precursor of the equality of the inequality average W greater or equal than delta F, right? Because since this is a convex function, okay, in general you will find that this is okay, here I'm going to mess up because I don't remember. I should have written it. Okay, you prove it yourself. I'll tell you after the lecture. I'm going to make a mistake if I write it now because I don't remember it and I get confused. But in okay, so this is smaller. Now this is greater or equal than e to the minus beta w. And that implies that. So you have to prove this inequality. Right. So, but in any case, usually when you are taught this in thermodynamics, these or similar inequalities for the production of entropy, etc., you're always told that when do you have the equality? You have the equality when the process is quasi-static, right? Because when the process is quasi-static, it means that you're staying at all times close to thermal equilibrium, and then eventually the work that you will be doing is equal to the difference in free energies between the final and the initial state, right? You remember that. So in a sense, the inequality has the meaning of telling you how much irreversible is your process, right? So the question we might have at this point is, can we figure out a way to study this irreversibility directly in terms of these probability distributions? And the answer is, of course, yes. And we will come to the so-called Tazaki-Crookes fluctuation theorem. So the Tazaki-Crookes fluctuation theorem says the following. Let me first state it, and then I'll prove it to you. It says that if I have a certain protocol that goes from some lambda initial to some lambda final, and I compute the probability distribution to do the work W, and I take the ratio of this with the probability to do work minus W in the inverse protocol, in which I go from lambda final to lambda initial, tracing back the time evolution, what I will get in general is that this is equal to e to the beta W minus delta F. So this is the statement. It's again another of these very general statements you can find in this field, both classical and quantum. So there is nothing specific to quantum dynamics in this. Now, why this has something to do with reversibility? First of all, you see that we are considering the protocol forward and backward with work W and minus W. Now, let us look at the quantity that is sitting in here. If you remember thermodynamics, you know that the entropy production in general has to be equal, greater or equal than minus the heat dissipated in the environment divided by T, right? The entropy that is produced in a certain protocol. And therefore, we can define sigma as excess entropy as the difference between the two. Now, if we use the first principle of thermodynamics, you can write this as 1 over T delta S plus W minus delta U, and then this is equal to 1 over T. You see that the delta U minus TdS is the free energy, so is the W minus delta F. So in practice, what we are doing here is stating that this is the exponential of sigma, of the entropy that is produced in general, right? if we apply this inequality, if we assume that we could apply this inequality also for open systems, etc., this is the statement. So it is something that has to do with characterization of irreversibility of a protocol. Yes?
And delta F is in our case is some strange quantity, right? That is, I'm like F final taken with temperature of the initial state,
Mm-hmm.
and I'm not sure that I can understand how it is working. So it is some measure, okay?
But this is true also in thermodynamics, right?
Of
So also in thermodynamics, you define entropy, etc., as state function. But in general, when you do a protocol, you will not do a work that is equal to. If it's reversible, you will do more work than what the state function would tell you, right? So, okay, take it as it is. Now let's prove it. Okay, let's prove it for our system and let's see how it works. So, what is this?
That is
How do I remove it? Ah, okay, thank you.
Can you remind us sigma has which meaning?
Which sigma?
Big sigma.
I don't know what I did.
well,
No. We lost everything? So the rest is still there?
It should be.
Ah, okay, good. So sigma, what is the meaning of sigma? The question. Well, it's essentially the entropy production over the protocol, right? Because
The physical meaning of this entropy production.
what is the physical meaning of this entropy production? I think it's just, it's like when you do the calculation of you remove a wall in a right? The free expansion calculation of a joule. Same story, right? So what you do there is you remove the wall, but you don't care about these states. The entropy that is produced, you compute it as a state function between final and initial state. The same story here.
We change parameters, system become partially distribute and have new entropy, and that's the change.
Right. So because the transformation is in general an irreversible transformation, you produce more entropy than what you would have if the transformation was done quasi-statically. So that's the statement, right?
Because here everything is reversible, right?
Sorry?
Here everything is reversible.
No, that's the point. It's not reversible.
Why? If we
Well,
change
be-
this parameter, we can change it back.
No, but okay, no, wait a second. Of course you can change the parameter back, but it's not clear that you will come back to the same initial state, right? Now, think about the two-level system, right? Even for the two-level system, I'll leave you this thing to think about. Landau-Zenner problem. So this is not a many-body system. There is no thermodynamic limit, nothing. It's just a two-level system. I start here. I time evolve forward in time and then backward in time linearly. So I do this. In time, I do, well, I don't know, this and that. Two linear evolution, two linear sweeps. I mean, this is inappropriate. It should be like that.
So we will not have a first state after we go.
So the question is, you start here, you evolve it, then you go back. Will you go back to the same initial state? No. In general, no. Can you make a protocol that will go back to the same initial state? Of course. You can take the inverse of the unitary evolution, right? But it's not clear that you will be able to write this inverse as a protocol for lambda of t, right? So that's the point. So in general, there is a unitary operator that inverts the dynamics, but it's not clear that you will be able to write it as something that an experimentalist can do. So that is the point. Okay, so now, Tazaki-Crookes, how do we prove it? So now it's thinking. Okay, let it think. How do we prove Tazaki-Crookes? There it is. So it's always the same story, always the same trick. So we know that Z of lambda initial to lambda final U is equal to trace U dagger e to the minus I H lambda final U e to the I H lambda initial U e to the minus beta H lambda initial divided by Z lambda initial. This is what I wrote before. Okay? Clear? So now let me compute Z of lambda I to lambda F minus U minus I beta. So this is equal to what? Is equal to trace of U dagger e to the I H lambda final U e to the minus beta H lambda final, and then U, and then e to the minus I H lambda initial U divided by Z lambda initial. Now I have to do the dangerous thing. Okay. Let it think. Okay. Good. So now I start using the invariance property of the trace, right? So I rewrite this as, well, I take out this Z lambda initial, I multiply and divide by Z lambda final, and therefore I can write this as trace of U e to the minus I H lambda initial U dagger e to the I H lambda final U e to the minus beta H lambda final divided by Z lambda final. Now, you see that this has exactly the same structure as this one, but this is another protocol. It's a protocol that goes from lambda final, so here I had lambda initial, here I have lambda final, all the way to lambda initial, right? And the U and the U daggers are inverted. So this is, in a sense, the inverse protocol in the sense, in the operatorial sense. So this is equal to, erase, Z of lambda final, Z of lambda initial, Z of lambda final to lambda initial, U. Okay. So let's go, no. Okay. So I will write, let it think. Think. Okay, good. So this was equal to Z lambda initial to lambda final minus U minus I beta, right? And now you see that, where is it? You see that here. you see that this equality implies that z of lambda initial to lambda final minus u minus I beta times z lambda initial is equal to z lambda final to lambda initial u z lambda final. Okay? So now, if you remember what z is, so is the average of e to the minus I w u with respect to p of w, you will get here that this is nothing but, well, what I wrote before. So it's p p lambda initial to lambda. Let's do it actually, because I don't like leave it here like this. So this is going to be the average of e to the minus I plus I w just a second. Okay, so this is integral dw pw e to the minus I w u e to the minus beta w equal to integral dw pw, the other guy, e to the minus I, actually here there is a plus, I w u, and then there is a z lambda I, z lambda f. And now, well, if you compare these two guys, you see that what you exchange, so this is lambda initial to lambda final. You exchange the integration here to w, from w to minus w. And now you compare these two expressions and you see that this is p lambda initial to lambda final w. Z lambda initial times e to the minus beta w equal to p lambda final to lambda initial minus w, z lambda final, and, well, the equality that the Tazaki-Crookes theorem follows from this. Okay?
I guess somewhere it should be minus I w u in the exponents, right? Either on the left, either on the right.
Where?
I guess on the right side. I mean, as far as we have u and minus u, then somewhere it should be minus u.
So here there was a minus.
Yeah, and I think that should be. No, no.
We redefined the.
Sorry?
You're correct.
I'm wrong. Right?
Now that we have a minus in the probability, there is a plus in the exponent.
So we change integration variable from.
No, so here there is a minus u, right?
Yeah,
So before I defined it as e to the minus iwu. So since here I have a minus, I put a plus here, correct?
yes.
And I put a minus here, correct? And now, but here there is a w. I change the integration here, and I get a minus.
W inside the argument. Okay.
Yeah,
I haven't seen the minus.
I change this w into a plus, and I get a minus w here. So I think it's correct. Okay, so this is the Tazaki-Crookes fluctuation theorem. Now, what is surprisingly interesting about all this stuff, and that's why I need my glasses, not just because I'm old, is that all of this story can be actually generalized from the case of this of quantum quenches, or in general protocols that are based on a certain Hamiltonian, to the more general case of a situation in which in between your initial energy measurement and your final energy measurement, you do whatever you want. You do unitary evolution with gates, you have a circuit, you start applying whatever you like to your qubits, you start doing measurements, etc., etc. Even if you do that, you will still get Jarzynski equalities, you will still get Tazaki-Crookes fluctuation theorems. Now, this is a very surprising, quite surprising statement. And what I would like to do now, if you're interested, is to extend it in this direction.
Can I first ask one question?
Yes.
So I'm a bit confused because, so does this theorem actually state that this time evolution is irreversible, or does it just state that in classical systems it's irreversible and this theorem is just has the same form for quantum systems? Because I thought that quantum evolution, when it's unitary, it's reversible.
Okay, so that's the same question. I don't remember who asked it, for you or you. So the point is this. Of course, quantum dynamics is reversible because it's linear, right? So the statement is, if you give me a unitary evolution, so if you give me a time-dependent Hamiltonian and the evolution in time is represented by this operator, then of course this operator has an inverse, the adjoint, because it's unitary, and that's it. It's reversible, right? The question is, here the question is not if it's reversible in a mathematical sense. The question is if it's reversible in an experimental sense, right? So in other words, imagine that I'm an experimentalist. I don't know how to invert operators, right? The only thing I know is to change a knob that changes a parameter in time, right? And my question is, if I start with some initial value of this parameter, I turn the knob, I go to this final value, and then I turn the knob back, and I go to the initial value with the same time dependence. Will I go back to the same initial state or not? And that is very non-trivial. It's not guaranteed that you will go back to the same initial state, right? So that is the type of irreversibility I think I'm talking about, okay? So it's a different, it's not an irreversibility in principle, because of course unitary dynamics is reversible, but is is more related to what you can do in practice, okay? All right, so now concerning extension to general systems, I will have to tell you briefly, since I'm going to do things in great generality, I'm going to tell you briefly how you represent a measurement in quantum mechanics, in many-body physics, or in general in quantum mechanics. Now, here I'm entering a field that is huge, so I'm going to tell you just a few things that I need for my proofs. But if you're interested in something more extended on this subject, my advice is to read the book by Wiseman and Campbell, which is called Quantum Measurement and Controlled in whatever, Quantum Optics. I don't remember precisely the name of the book, but it has to do with quantum measurement. Now, the point is the following. Of course, I mean, you're used to, when you're told that you, I mean, in standard textbooks on quantum mechanics, measurement is represented typically by projectors, right? So you have a spin, you want to measure whether it's spin up or spin down. You have your projector, pi up, which is up, up. Your projector, pi down, which is down, down. And then, of course, the expectation value on the quantum state of your favorite projector represents the probability to measure that state in a practical measurement. And after you do the measurement, of course, you have the projection postulate that tells you that you have to modify your state accordingly. So if your measurement is successful, your new quantum state, psi plus, is going to be the projector applied on your psi, on your state before the measurement, divided by the probability, the square root of the probability to measure the eigenvalue or whatever the state I, the eigen, the observable, whatever. The outcome is the correct word, outcome I, for your measurement. Okay? Of course, you can generalize this to something that are known as generalized measurement. In practice, in physical systems, you almost never do projective measurements, right? In quantum optics or in other fields, you do generalized measurements. Generalized measurements, and you can read about them in this book. The first chapter is all about representation of measurements in quantum mechanics, can be represented using something known as Krauss operators. So you imagine having a set of operators, M of R. They don't need to be unitary, they don't need to be self-adjoint, they don't need to have any particular properties. The only property they need to have is that they need to satisfy sum over R. R here represents the possible outcomes of a measurement. Sum over R, MR, M dagger of R equal to 1. So they need to resolve the identity in that sense. But they don't have to have, in general, any other property. So let me make an example. Of course, projective measurements fall into that class, right? But another type of measurement that does not fall into that class is, for example, when you have a cavity and you want to measure the occupation of photons, right, by a photodetector. So in that case, your M of R is going to be this, 0 R. So it takes, if you have R photons in your cavity, you measure that you have those R photons, and then the state is reset because your photons are all absorbed by the apparatus. Now, you see that this is not a projection operator. Now, if you take, no, actually, now I see that I made a mistake here. If you take M dagger of R, M of R, this is equal to R 0, 0, R, and you sum it, and you get the identity because it's the sum over all possible occupations of your cavity. But notice that this is not, the opposite equality is not true, right? Because if you take the adjoint of this operator, you will get from this that this is equal to 0, 0. And this is because you reset your 0, 0 times, times sum over R. Let's be honest.
Projector on zero. Probably.
Sorry?
Projector on zero state probably. Not bracket, but
Okay, let me do it slowly. Okay, so let me not guess it, but do it. You will get that this is equal to sum over R. You will get 0. Yes, you're right. R, 0. And then you will get sum over R, 0, 0. So, well, that's what it is. A number, if you have an upper cutoff to the number of photons, you will get a number times the projector on 0. Good. So now what is the, okay, so this is the general representation of measurements. What should I do? It's 11:30. Can I go on for a few seconds? Okay. No. Right.
Can you slowly remind the version? How is it connected with the previous two theorems that we proved?
So what I'm trying to do now is the following. So in the previous theorems, I just took an Hamiltonian that had a time-dependent parameter. And I time evolve it, and I check what is the work that is done, what is going on, right? So what I want to do now, and maybe I'll just state the problem and then we do it afterwards, is the following. Imagine now that I have a general time evolution. I don't have anything specific in the middle. What I do is, I have the following protocol. I do an energy measurement of a certain initial Hamiltonian at a certain time, initially. Then I time evolve my system with a generic time evolution. The generic time evolution could be the following. So let me represent it graphically. I have a set of gates on my elementary degrees of freedom plus eventual measurements. They don't need to be done even on all gates, on all systems, I don't care. And then other gates, other measurements, etc., etc. Something generic in between. So it's just a bunch of unitary gates. You decide how you generate them and measurements. So in practice, this will mean that the evolution that I will do from my initial state to the final state will be described by an operator that is going to be a bunch of unitary operators. Sorry, I'm messing up. So the first one that goes from t initial to t1, and then here I do a measurements mr1, and then I do another evolution with another unitary operator that is generated some way, and then I do another measurement, MR2, etc., all the way to the final evolution. Okay, well, something general. Measurements and unitary evolutions in the middle. And then, after I do all this mess, I measure H lambda final. So I measure the eigenvalue of some final Hamiltonian. The statement is, if I started in equilibrium at inverse temperature beta with my initial Hamiltonian distributed according to a Gibbs distribution, then this evolution, this general evolution will still satisfy the Jarzynski equalities. Even though here in the middle, I have everything but Hamiltonians. So you see, coming to your question here, even talking about irreversibility in the sense of, I have an Hamiltonian and I find there is no Hamiltonian here. There's nothing. There's just a bunch of operators that you need to represent using a circuit. So the statement is you will still find the Jarzynski equality. Okay? So, and I will prove it to you, and I will show you that you can use this story to define something known as quantum trajectories, and then summing over all trajectories, you will get the Jarzynski equality. And yes?
Microscopically, I guess we have some quantum dynamics of this Hamiltonian
Of?
of the system of the circuit, because
Well,
it's a quantum world in any case, right? Will function.
okay, so the reason I'm thinking about it this way is that I'm not thinking anymore about, so you're right. I mean, if I look at the table is quantum. It has a quantum dynamics. But what I'm thinking about is a digital simulator of something, right? So I imagine representing the dynamics using a quantum computer that applies a certain gates on a register of qubits and certain measurements. And the statement is, even if you don't have a real physical system, but you have a digital quantum computer that represents the dynamics, it will satisfy the Jarzynski equality, provided you start in thermal equilibrium. Okay? So it's a very non-trivial statement, in my opinion.
How we can check an experiment?
Levioff and Misha Fegelman can check with Google. So you here, you can check everything in Ljubljana. I don't know. I mean, you need to use a digital quantum computer, represent it, do the measurement, check the statistics. Yeah, it can be done in principle, right? So I will show you how to prove it. You will understand what are the details, and then you have to check it. Actually, so this result here is actually pretty new. It's something that we published last year. So actually this year, not last year. So, but it's nice. It's a generalization of everything to the most general case. Okay? So we will see it later.